All right, let's get started. I'm going to have you copy this triangle down. This triangle is a ramp or some type of incline, and this ramp is angled above the ground with some angle theta, and then we have an object that is on top of the ramp. In this case, the object is sliding down the ramp at constant speed. So in the case of Newton's second law, this would mean that there are no net forces. No net force. Not net forces. There's no net force on the block, but there are still forces acting on the block. They just all cancel out. Okay, so we are going to analyze the forces on here, and the first one you always start by drawing is the main one, the one that actually sends the object down the ramp. It's the reason the object would even slide down the ramp, and it is the object's weight. Its force of gravity, the object's weight, W-E-I-G-H-T. So I want you to put a little dot in the center of your object because that is the object's center of mass. You draw your arrow straight down from the center of the object to the center of the earth, and we are going to call this W for the object's weight. Just so you remember, W equals mass times little g, 9.81. Now, the reason the object doesn't accelerate down to the center of the earth is because of the normal force that is acting on the object. The normal force is normal to the surface, perpendicular. It is at a 90-degree angle with respect to the surface. This is 90 degrees. And it extends up from the plane of the ramp, from the surface of the ramp, out of the object upwards. And I'll call this the normal force, capital R, for normal force. Now, if we were on a flat surface, I'm going to show you the GeoGebra here. If we were on a flat surface, the normal force would be equal and opposite to the weight, the object's weight. But we're on an incline. And so what happens is the normal force changes. The magnitude of the normal force changes because the normal force stays perpendicular to the ramp or to the surface. And it is only a small component of gravity, a smaller component of gravity, that gives rise to the normal force. I'll show you over here back in the PowerPoint. So to figure out what the value for the normal force is, I am going to extend a line right here. And then this vector, this is equal in magnitude, opposite in direction. And I'm just going to call this negative r. This value for the normal force is one component of the weight vector. So in this case, my weight is like this hypotenuse of a triangle. And the angle between the negative r, the opposite of the normal force, and the weight vector is equal to the angle of incline. So I'll get rid of this perpendicular symbol. And I'll note that this angle here between the two is equal to the angle of incline. That's actually what you saw in that diagram here. As I rotate this angle here matches the angle between the weight vector and the opposite of the normal vector. They rotate together as you increase the angle of incline. Gravity always stays pointing down, and the normal force is always normal or at a 90-degree angle to the surface of the ramp. So the angle between the gravity vector and the opposite of the normal force equals the angle of incline. It's okay if you don't fully understand right now, but as long as you memorize this and you'll practice, you'll get better. Just memorize for now that this opposite of the normal force, the angle between the opposite of the normal force and the weight vector is theta. This weight vector is the hypotenuse for a vector triangle. The weight vector is the hypotenuse. The normal force then is a component of the weight vector. If the weight is my hypotenuse, and I have this opposite of the normal vector. It's equal in magnitude, opposite in direction. I'm going to have some other force here. We'll label it later, but right now I'm going to solve for the normal force, or the opposite of the normal force. This is theta, and this is W. The W is my hypotenuse. I have an angle that is adjacent to one side of the triangle. So I have an adjacent side, that's this guy, adjacent. The weight vector is my hypotenuse, and I have an angle. I'll use cosine. Cosine of theta, SOHCA TOA, is equal to adjacent side, the adjacent side of the triangle, divided by the hypotenuse. The adjacent side is the negative r vector. And I will divide by the hypotenuse, by the weight. And so negative r equals W cosine theta. If I solve that, it's W cosine theta. That means the normal force has the exact same magnitude, just opposite direction. It's also W cosine theta, or mg cosine theta. So on a ramp, the normal force acting on the object is a small component of the weight. It is mg cosine theta. Now, the reason the object accelerates or slides down the block is because of this other part of the vector triangle. The the force of gravity splits. It splits perpendicular to the ramp, and it splits parallel to the ramp. So I'll label this in green. And I like to call this force down. And I'm going to translate this vector up here. Oops, this should be parallel to the surface of the ramp. Be very careful, guys. So many students lost a lot of points last year because when they drew this force down the ramp, rather than being parallel to the surface of the ramp, they had it parallel to the ground, to the bottom of the ramp. That's not the direction the object is sliding in. Do not draw the vector like this. The vector is parallel to the surface of the ramp. The object is sliding parallel to the surface of the ramp. It is not sliding in this weird, crazy fashion. Parallel to the surface of the ramp, not parallel to the ground. It's still on the ramp. All right, so this is the force down. Let me clear up some space here. I have to stress this. Please don't make that mistake. You will be quizzed on drawing this. Okay, so in this vector triangle now, this is my force down. Clean this up so we can focus. I have my weight, which is the hypotenuse. I have this angle between opposite of the normal vector and the weight vector, and then I have this force down. The force down is opposite to the angle. It's on the opposite side, and I still have my hypotenuse, which is the weight vector. In opposite side, I have an angle, I have the hypotenuse, so that's sine. Sine theta is equal to opposite over hypotenuse, SOHCA TOA. But you're given the trig formulas in your data booklet. I'm going to look for my opposite side, so that's the force down, which I'll just simplify as F sub D, force down divided by the weight. So that means force down is equal to W sine theta. Force down equals W sine theta. Force down is also equal to mg. If I substitute out the W, it's mg sine theta. If this ramp were frictionless, the object would accelerate down the ramp. but the object is sliding down the ramp at constant speed, which means there can be no net force acting on it. That means this object, this ramp, has to have friction. There's friction acting between the surface of the ramp and the bottom of the block. Because it travels down at constant speed, this force down the ramp must equal an opposing force. I will draw this. This is the force of friction going up the ramp. It is equal in length to the force down the ramp, opposite in direction. Equal in magnitude, opposite in direction. That's the force of friction. This is why the object travels down the ramp at constant speed. It matches the force guiding the object down the ramp. Force of friction has its own equation from the data booklet. Force of friction is equal to mu times r. And I could go one step further. Force of friction is equal to mu mg, mu being the coefficient of friction. The weight vector we solve for here, mg cosine theta. So it's mu mg cosine theta. So hopefully you followed along with this video. This is the first time you're doing this, but it is not the last time. Thanks for watching, guys, and practice this. Try to draw this a few more times over and over until it's just second nature. Study well.